Hi all, today we're going to go through topic 10, rate laws in order of reaction. We're going to split this lesson into two parts. First part just trying to understand what rate laws in order of reaction is, and then the second part will be going through trying to figure out what the order of the reaction is with respect to the reactants using raw data. So for the first part, just trying to break down what a rate law is and what order of reaction is and what information we get from it. So the learning goals for this entire package is to determine the rate of a reaction using rate laws, and to determine the order of a reaction with respect to a reactant and or products, as well as the total order of reaction, and explain the significance of these on the reaction rate. So we know that increasing the temperature or initial concentration of reactants can have an effect on the speed of a reaction, but we don't know by how much. There is actually a mathematical relationship, a pattern between reaction rate and the various factors that do affect it. This pattern cannot be predicted just from theory. An experiment needs to be done to figure this out, and it's only through experimental evidence that we can figure out the impact of these different factors. So if we look at this balanced equation where we have nitrogen monoxide reacting with oxygen gas, so we have 2NO plus O2 yields 2NO2. So we're going to use this to start examining these relationships. So it seems logical to say that the rate of a reaction depends on the concentration of each of these reactants. But which one has a greater effect? Or do they have an equal effect? So does the concentration of NO have a greater effect on the reaction rate than the concentration of O2? Now notice here this notation that's used where you have square brackets and then the chemical written in between. What that means is it's the molar concentration of the entity that's specified within the brackets. Okay, so it's just another way of trying to indicate molar concentration rather than using capital C. It's a little bit more of an easier way to be specific in terms of which chemical in the reaction you're dealing with. So going back, our question is, but does the concentration of NO have a greater effect on the rate than the concentration of O2? We cannot know that just by looking at the balanced equation. And it's only experimental evidence, not theory, that can actually answer that question. So experimental evidence suggests that the rate of a reaction is exponentially proportional to the product of the initial concentrations of the reactants. So let's imagine a chemical reaction in which A and B are the coefficients used in balancing the equation, and X and Y are the formulas for the reactant molecules. So here we have our reaction. So we have X reacting with Y to make some products. And the equation is balanced using coefficients lowercase a and lowercase b. So rate law says that the rate of a reaction will always be proportional to the product of the initial concentrations of the reactants. We don't care about the products. It is only the reactants that we're concerned with, which is why we didn't write out the products on this hypothetical equation. So the rate will always be proportional to the product of the initial concentrations of our reactants, where those concentrations are raised to some exponential value, which is going to be called the order. And we'll talk a little bit more about that in a moment. So this can be expressed as this mathematical relationship, where R, the reaction rate, is proportional to the concentration of the reactant. So in this case, we have two reactants, X and Y. And we're using our square brackets to indicate that we're saying that the concentration of those, and it's raised to some kind of power. So some hypothetical power. In this case, it's X is given to the power of M and Y is given to the power of N. So for any reaction, we can go and say that the rate of that reaction is going to be dependent on the initial concentrations of the reactants raised to some kind of power. So if we take that a little bit further, the M and N, as we said, those are the exponents that describe the relationship between the rate and the initial concentration. And those can be only determined experimentally. And we're going to learn how to do that in part 2 of the lesson. For now, we're going to be given that information in all of the problems that we're going to do. So they can have any real number value, including fractions, and do not have to be equal to the coefficients in the balanced equation. Okay, these are things that are determined empirically through the experiment, and we will be figuring them out as we work our way through part 2. So those exponents are called the order of the reaction with respect to those reactants. So our rate law expression can be rewritten as an actual equation. When we're converting a proportionality statement to an equation, we have to introduce a constant. So we can rewrite this expression to say that the rate of a reaction is equal to some constant, which we're going to call the rate constant, times the concentration of our reactants raised to some kind of a power. And in this case, because we said we had two reactants, X and Y, so it's X in square brackets raised to the power of M times the concentration of Y raised to the power of N. Okay, the rate constant is determined experimentally, just like the orders of the reaction, and they're only valid for a specific reaction at a specific temperature. As soon as you change any of the conditions besides the concentrations, the value for K will change. Okay, so you're going to find that whenever we're carrying out reactions, we're going to keep the conditions constant as we're working our way through. So now that we've explained what the rate law equation is, we're going to go back to that initial reaction that we were looking at earlier. So we have 2NO2 plus F2 goes to 2NO2F. So the rate law expression for this reaction, determined empirically through experimental evidence, was R is equal to K, the concentration of NO2 to the power of 1, times the concentration of F2 to the power of 1. So in this, the rate depends equally on the initial concentrations of each reactant, where M is equal to 1, which refers to the order of the reaction with respect to NO2, and N, which is the order with respect to F2, was also 1. Now notice that even though we look at our balanced equation, we have 2NO2 and F2, the coefficients do not come into play. So through experimentation, scientists have found that the concentration of NO2 and F2 both have an equal impact on the overall rate of this reaction. Now, the orders of the reaction are, as we kind of indicated earlier, the exponent value that describes the initial concentration dependence of a particular reactant. So going back to this reaction order, this rate law expression, we have R is equal to K, concentration of NO2 to the 1 and F2 to the 1. The order of this reaction with respect to NO2 is 1. The order with this reaction with respect to F2 is 1. Now, the overall order of the reaction is simply the orders of these reactions added together. So in this case, we have 1 plus 1. The overall order of this reaction is 2. Now, what does this information give us? Because it sounds pretty theoretical at this point. So, as we're going through, let's try to look at another example. If we perform a series of experiments with different initial concentrations of the same reactants, we could use the orders of the reaction to predict the reaction rates. So let's say we have this reaction here where we have X reacting with Y and Z, and they're balanced using coefficients of 2, 2, 3. But we don't really care about that for this. So we are told experimentally that the rate law expression for this reaction is R is equal to K, the concentration of X raised to the power of 1 times the concentration of Y raised to the power of 2 and the concentration of Z raised to the power of 0. What would the total order of this reaction be? If you thought 3, that's correct. It is 1 plus 2 plus 0, which gives us 3. So now, let's see what the order of the reaction tells us. So in here, because the rate of the reaction is proportional to the concentration of X raised to the power of 1, if the initial concentration of X is doubled, the rate of the reaction will also double. Okay, so we can multiply by 2 to the power of 1. Okay, so in this case, we're doubling the concentration of X. If the initial concentration of X is tripled, then the rate of the reaction will also be tripled because we're multiplying the rate by 3 to the 1, which is 3. Similarly, for Y, because the rate of the reaction is to the order 2 for Y, if we double the initial concentration of Y, the reaction rate will multiply by 4, or it'll quadruple, because we're multiplying it by 2 to the 2, because the order is 2, which gives us a multiplying factor of 4. If the initial concentration of Y is tripled, then the rate of the reaction will multiply by 9, because it's 3 to the power of 2. Similarly, for Z, the rate does not actually depend on the concentration of Z. All that matters is that it's there. Because if we go through and we double the initial concentration of Z, the rate will be multiplied by 2 to the power of 0, which means that it's going to be unchanged. Please correct this. It says it's multiplying by 0. It should be multiplying by 1 because it remains unchanged. If the initial concentration of Z is tripled, the rate will multiply by 3 to the 0, which is 1. So please correct that. It should not say 0, it should say 1. So the rate will be unchanged. So changing the concentration of Z will have no impact on the overall reaction rate. And as we indicated before, the overall order of this reaction is 3. So as you can see, if we have the rate law expression, we can predict how changing the concentrations of each of the reactants will impact the reaction rate. Now, the units for K are a little bit tricky, which is our rate constant. The order of a reaction can be determined from the units of the rate constant K. Okay, so the reason why it's a little tricky is if we look at it a little bit closer. So the rate of a reaction is always measured in moles per liter second. So if we go through and we look at a first order reaction, so here we have an expression that is the rate is equal to K times the concentration of A raised to the power of 1. Okay, so our overall order of reaction is 1 in this scenario. And what we're going to do is some unit analysis, where I'm going to plug in the units for each of these entities. So our units for rate are always going to be moles over liters second. So that's equal to K, and we're going to try to isolate for the units of K. And the units for concentration are moles per liter. Okay, so now what we're going to try to do is just try to cancel these out to figure out what the units are going to be. So what I did was I just moved these around where I moved moles down here and liters up to the top. And now if we do that, we can see that our moles cancel out, liters cancel out, and our units for K are going to be 1 over second. Okay, so if we have a total order of a reaction of 1, the units for K, the rate constant will be 1 over second. Okay, now let's look at some other scenarios. So below, we're going to see the steps to solve for the rates for orders outside of 1. Okay, and we're going to see that the units for K will need to change to cancel out the units for concentration to allow us to have that the rate of a reaction will have units of moles per liter second. And we're going to also notice an easy trend that we can use at the end to figure it out instead of doing all of this unit analysis. So we already solved for the first example here. This is just another way of rewriting it. So let's look at another one. So here, if we have a total reaction order of 2, we can go and say, okay, our rate law expression is R is equal to K, the concentration of A raised to the power of 2. So I'm just plugging in my units. So the units for rate are moles per liter second. We're trying to solve for K. The units for concentration are moles per liter. And because it's order 2, I'm going to have an exponent value of 2 here. And what I did was I just distributed this unit 2 to each of my entities inside the brackets. So I have K and then moles squared over liter squared. And now if I go through and isolate for K, so basically all that I did was I moved my liter squared up here and moles squared down. And now if we do that, we can see that the moles here cancel out and I have moles on the bottom. And then my liters squared here now becomes liters, and this liter cancel out. So I have units for K of liters per mole dot second. Okay, notice how the units are different from order 1. Okay, now we're going to go and look at a total reaction order of 3. Okay, and we're going to notice a little bit of a trend. And like I said, we do not need to use unit analysis every time. We're going to just look at our chart to figure out what it's going to be. Okay, so in here, if we have a total reaction order of 3, we have R is equal to K concentration of A to the 3. And I'm plugging in my units. So for rate, it's moles per liter second. For concentration, it's moles per liter. If I factor out the 3, I have moles cubed, liters cubed. And now if I isolate for K, I get K is equal to liters squared over moles squared second. Okay. Now, do you notice a trend as we work our way through? As we go from order 1 to 2 to 3, we're adding 1 liter per mole every time. Okay, so if we look at reaction order 4, the units for K are liters 3 over moles 3 per second, dot seconds, sorry. If we have total reaction order 5, it's going to be liters 4 over moles 4 seconds. Okay, so we don't need to memorize this. What I'd recommend is that you write out a chart, and then every time we're doing a problem, you just figure out what the overall order of the reaction is and write out what the units are going to be. Okay, I do not expect us to do the unit analysis, but you should be able to tell me what the units for K are. And I just want to specify just again why we need to do this. So as we're going through, the units for K are always going to change because we need to make sure that the units for rate are always moles per liter second. And as we have different exponents, and because the units for concentrations are moles per liter, we need to be able to cancel that out. And by having different units for K, that will allow us to have units for rate of moles per liter seconds. Okay, so let's try some sample problems so we can actually see how we can use rate law equations to figure out rates of reaction and how changing the concentration of different reactants will impact the rate. Now, if we look at this problem, it's going to be a mouthful, but what you're going to find is that it's actually giving us a lot of information. So in here, an investigation indicates that the initial rate of the reaction represented by the equation. So here we have BrO3 minus reacting with Br minus and 6H plus, and it makes liquid bromine and water. Now, in the question, we're told that at 25 degrees, the reaction rate is 3.2 times 10 to the negative 3 moles per liter second. Now, it is that rate when the initial concentration of bromate is BrO3, bromate BrO3 minus is 0.1 mole per liter. Initial concentration of bromide is 0.1 mole per liter. And the initial concentration of hydrogen is 0.2 moles per liter. Now, in the question, it's telling us that the reaction is first order with respect to bromate, first order with respect to bromide, and second order with respect to hydrogen. Now, we want to figure out the initial rate of the reaction if the concentration of hydrogen is doubled, with no change in the concentration of the other reactants. Additionally, we're asked to solve for the rate constant K. Okay, so let's see if we can try to break this down. So all I did here was rewrite the information that we know. So we know the rate is 3.2 times 10 to the negative 3 moles per liter second. We know the concentration of bromate was 0.1 moles per liter. The concentration of bromide was 0.1 moles per liter. And the concentration of H plus was 0.2 moles per liter. Now, we can write out a generic rate law expression. So the rate is equal to the rate constant times the concentration of each of the reactants raised to some power. So here I wrote R is equal to K, the concentration of bromate raised to the power of M, the concentration of bromide raised to the power of N, and the concentration of H plus raised to the power of P. And those are just the standard terms that we're going to use. Usually it's Mn and P, and we usually won't have more than 3 reactants that we're dealing with. Now, in the question, it told us that it was first order with respect to bromate, so M is equal to 1. It was first order with respect to bromide, so N is equal to 1. And it's second order with respect to H+, so P is 2. So I can rewrite this rate law expression to be R is equal to K, the concentration of bromate raised to the power of 1, bromide raised to the power of 1, and the concentration of H+ raised to the power of 2. Okay? And we're asked to solve for the rate if the concentration of H+ is doubled, with no change in the concentration of the other reactants. Okay, now, the nice thing about having the rate law expression, it allows us to solve this pretty simply. So we know that since this reaction is second order with respect to H+, if its concentration is doubled, just like we saw in some of the previous problems, the rate of the reaction will increase by 2 to the power of 2, because we're doubling the concentration, and the order with respect to H+ is 2. So the rate of this reaction is going to increase by 4 times. So all I'm going to do is take the initial rate that we had of 3.2 times 10 to the negative 3 and multiply it by 2 to the 2, or 4, which gives us a new rate of 1.3 times 10 to the negative 2 moles per liter second. Okay, so we can use this to figure out how changing the concentration of one of the reactants impacts the overall rate of the reaction. Now, the second part of the question asks us to solve for the value for K. And all we need to do is plug in the values that we have. So initially we were told the rate was 3.2 times 10 to the negative 3, and we were told the concentrations for bromate, bromide, and hydrogen. So we have our rate law expression, R is equal to K, concentration of bromate to the 1, bromide to the 1, and H+ to the 2. I'm isolating for K, so all I'm doing is dividing by these values over here. So we have K is equal to rate times the concentration of bromate to the 1, bromide to the 1, and H+ to the 2. I plugged in the values that we had from one run, and then we solve for the value for K. Now, in here, because the overall order of the reaction is 4, we have 1 plus 1 plus 2, so it's 4. Our units for K are going to be 1 less than that. So we have liters 3 over moles cubed dot seconds. Okay, so we can always use the total order to figure out the units for K. Now, after this, you're going to notice another more detailed breakdown. If you want a little bit more of a step-by-step guide, it does provide it, but I'm not going to go through it. You can read through that on your own time if you'd like. What I'd like to do is try to go through sample problems 2 and 3. So in sample problem 2, it says the decomposition of dinitrogen peroxide, written out by this expression, 2N2O5 yields 2NO2 and O2, is first order with respect to N2O5. So if the initial consumption is 2.1 times 10 to the negative 4 moles per liter second, so that's just the rate, it's just another way of trying to write that out. When the initial concentration of N2O5 is 0.4 moles per liter, it's asking us to predict what the rate would be if another experiment was performed in which the initial concentration of the reactant N2O5 was 0.80 moles per liter. So let's write out our rate law expression. We always need to start off with that. So we have R is equal to K times the concentration of N2O5 raised to the power of 1. Now it is to the power of 1 because we're told that it is first order in the question. We're told that the initial rate is 2.1 times 10 to the negative 4 moles per liter seconds, and that the initial concentration of N2O5 at that reaction rate is 0.40 moles per liter. The question is asking us to solve for the rate if the concentration of N2O5 is 0.8 moles per liter. Now, if we look at this, you'll notice that we're actually doubling the concentration of N2O5. Now, since the concentration of N2O5 is doubling, the reaction rate will increase by 2 because the reaction is first order with respect to N2O5. So all we're doing is multiplying the initial rate that we had by 2 to the power of 1. Okay, and that gives us a rate of 4.2 times 10 to the negative 4 moles per liter second. Okay, if the concentration was tripled, then we would just multiply by 3 to the 1. Now, sample problem 3. The dimerization reaction of buta-1,3-diene. The good old days of organic chemistry. So here we have 2C4H6 yields C8H12. And we're told that it's second order with respect to C4H6. So we're told if the initial rate were 32 millimoles C4H6 per liter minute, notice the units have changed, but that's not going to change anything in our calculation. At a given initial concentration of C4H6, what would the initial rate of reaction be if the concentration of C4H6 were doubled? So we can go through and write out our rate law expression. R is equal to K times the concentration of C4H6 to the power of 2. So our overall order of this reaction is 2. We're told that the rate is 32 millimoles per liter minute, and we want to solve for the rate if the initial concentration is doubled. Now, we're going to do the same thing as the last one. So since the reaction is second order with respect to C4H6, if you double its concentration, the rate would increase by 2 to the 2, or 4 times. So all that we need to do is multiply the rate that we're given by 4, or 2 to the 2, and that gives us 128 millimoles per liter minute. Don't worry about sig figs for these types of problems. We can just write out what we're given. That's not a problem for this. We're going to stop there. That's going to be the end of part 1. In part 2, we're going to go through and try to figure out how those order of reactions were determined. Your homework is going to be trying to write out rate law expressions, where you're going to be taking the balanced equations and going through and writing out expressions like we saw here. R is equal to K times the concentration of our reactants. We're going to be told the orders of the reaction, and that's going to tell us how each of these reactants impact the overall rate. And we're going to be asked to see, okay, if we change the concentration of these reactants, what impact will it have on the overall rate? And we're going to do similar analyses that we saw here in sample problems 1 to 3 to those problems. There are solutions posted on EDSB if you look in the folder that goes through and walks you through the problems as well from the textbook. Thank you.